So I'll write it out again. We have our Lagrangian is equaling our half mx dot squared. Okay, and they're going to add a quarter mr squared theta dot. Remember that our rotational kinetic energy was a half I theta dot squared. I was a half mr squared, and we just times the halves together to get a quarter. So we get a quarter mr squared theta dot squared. Okay, and then we minus mg. We're going to factor out our mg. We're going to get L minus our x sine alpha. Okay, so there's a Lagrangian. Now, if the disk does not slip, okay, let's make things easy, okay? If the disk does not slip, the distance it has travelled, x, is equal to the arc length of the disk that it has touched the inclined plane. Because if you think about it, as the disk rolls, the distance it has moved is also going to equal the circumference, well, you know, the arc length that has touched the inclined plane. Okay, so we need to find equation of constraint. Our arc length is equal to r theta. Okay, our arc length therefore is going to equal our distance x. So if we get the diagram quickly again, this distance x is going to equal the arc length, which is r theta. Alright, so that's our equation of constraint. Therefore, we get x dot, we just differentiate, is equal to r theta dot. And we can rearrange for theta dot is going to equal x dot divided by r. Okay, we want to get rid of theta dot. That's in polar coordinates. We're not going to do polar coordinates today. Okay, so 1 revolution is theta, which is equal to 2 pi. Okay, so our circumference is going to equal 2 pi r. Alright? So if the disk rolls 1 revolution, x is going to equal the circumference of the disk. So our Lagrangian, therefore, is going to equal our translational kinetic energy, a half mx dot squared, plus a quarter mr squared. Now we have theta dot squared. Well, use this equation, and we're obviously going to get x dot divided by r all squared. Alright? And then, of course, we can add our mg, change these signs around to get our plus, so it's going to become x sine alpha minus L. Okay, we just switch things around to make that a plus. You don't have to do that, it just makes things easier. So we can do some more stuff with this. We get a half mx dot squared, add our quarter mx dot squared, because the r squareds cancel each other out. Okay, so we're just left with mx dot squared. Alright, and we add our mgl x sine alpha minus L. Alright? So, oh look, we have mx dot squared and mx dot squared. So, we just need to add the terms together. Simple as simple as pi. So that's going to equal 3/4. A half plus a quarter is 3/4. Mx dot squared. And then we add our mg x sine alpha minus L. So look how simple that term is compared to our original Lagrange we had up there. It's a lot simpler. We can work with it. using the Euler-Lagrange equations, which we're going to do right now. So, in case you've forgotten, our Euler-Lagrange equation says that the partial of our Lagrangian with respect to our position is going to equal the rate of change of the partial derivative of L with respect to our velocity x dot. Okay? Right, so x. Where is x in the Lagrangian? Obviously, that's x dot, so that's going to become a constant. We have x on this side. So, therefore, this is going to become d by dx of mg, basically this term here, times x sine alpha minus the Lagrangian, okay? That's what we're taking a derivative of, because that's a constant. Okay, we want to involve x, not x dot. Alright? I'm going to minus the rate of change of dl by dx dot. Okay, so d by dx dot of what? It's just going to be 3/4 mx dot squared. 3/4 mx dot squared. Okay? So, if we differentiate this with respect to x, what we're going to get? So, we're going to get mg x sine alpha minus mg times L. Okay? So, this is going to become mg sine alpha. Okay? So, just to make things more explicit, I'll just quickly expand this. We get mgx sine alpha minus mgl. mgl is a constant that has no x terms in it. So now we're left with x multiplied by mg sine alpha. Mg sine alpha is a constant, and if you remember, if we differentiate a constant multiplied by our variable, we get the constant back. The variable that we're differentiating with respect to, we get mg sine alpha. Okay? And by the way, that's the force. Force equals mg sine alpha. Alright, so yeah, we've got that term now. We get mg sine alpha minus, okay, we've got a lot of stuff going on here. Differentiate this term with respect to x dot, use the power rule, bring that 2 over, and multiply that by the 3, we get 6 divided by 4, which is, yep, and then we take the time derivative of the partial derivative of x dot. So what we're going to get is minus 3/2 mx double dot. Okay, and that's going to equal 0. But yeah, so that term here is 0. So let's go over that. Use the power rule, bring that 2 over, we get 6 divided by 4, which is the same as 3/2. So we have 3/2 mx dot. Then we differentiate 3/2 mx dot with respect to time. We're going to get 3/2 m double dot. Okay, differentiate our velocity, get acceleration. X double dot is our acceleration. So there's the equation of motion. Excellent. So just tidy things up a bit. We can say that we can cancel out a couple of terms. We can cancel out our m's. Okay, and we're left with g sine alpha is equal to 3/2 x double dot. Okay, so therefore our acceleration is equal to 3/2 x double dot, because f equals mg sine alpha. So therefore, if you divide, yeah, so force is equal to ma. Divide by our mass, we get acceleration is g sine alpha, but g sine alpha is 3/2 x double dot. Therefore, acceleration is 3/2 x double dot. Alright, so there is the equation of motion for a disk rolling down an inclined plane, bearing in mind it's not slipping as it rolls. So there you go. I'll see you in the next video. Oh, and well done if you got that.